right, so today we're going to talk about dynamic programming. We're going to look at a particular dynamic programming problem, and we're going to explain what the difference is between a situation where you can use a greedy algorithm, which we'll always want to if we can, since it makes our code much simpler, it will run faster, and situations in which we can't make the greedy choice and we have to use dynamic programming instead. So a good way to get a handle on when dynamic programming has to be used and when we can make the greedy choice I like to use is this example of a trip from Metro Tech up to Yankee Stadium. Now, we could imagine one specification for the trip where you've got to pass through Grand Central Terminal on the way. Let's say, for instance, your friend is at Grand Central, and you've got to pick up your friend and then make it to Yankee Stadium somehow. So I've given you a constraint. You've got to get here. Well, you can now make the greedy choice from Metro Tech to Grand Central Terminal because essentially we can apply an economic concept here to say why. There's no opportunity cost to making the greedy choice here. What we have not constrained ourselves, we haven't lost any of the possibilities from getting to Grand Central to Yankee Stadium. So let's say it happens that your other friend is at Metro Tech with a fast car. Well, you can just get in the fast car and go to Grand Central. And at that point, all the possibilities from Grand Central to Yankee Stadium are still open to you. That's what we mean by saying this choice has no opportunity cost. You didn't give up any options here. No one is going to say when you arrive at Grand Central that, well, you came by car, therefore you can't take the subway. Or you came by car, therefore you can't get a taxi. All the choices are still open to you as to how to proceed from here to here. On the other hand, if we remove this constraint, now you can't make the greedy choice. For instance, we might characterize the greedy choice by saying the choice that gets you as close to Yankee Stadium as fast as possible. So the greedy choice here might be your friend with the fast car says, well, I'm going to Queens, and that's close to Yankee Stadium where I'm going, I'll drop you off. Well, you get in the car and take the ride to Queens and get dropped off and find out that you're now in some deserted part of Queens, there's no subways nearby, no cabs around, no ferry, and what you've done is there was an opportunity cost to this choice. You had to forego many other routes that would bring you towards Yankee Stadium, but then leave you with good transportation options. So it's because of the fact that you had to forego other options to take this ride that means we can't use a greedy algorithm here. We can't make the greedy choice. So we're going to look at a dynamic programming problem. It's similar to the activity scheduler in the greedy algorithm chapter of our textbook. But what we've done differently is we have a series of events. People want to book your auditorium. And you can book it on the hour, and each event is going to run 3 hours. This is much like the activity selection problem. The difference here is that we've now given prices. Different people are making different bids for how much they want to pay for the auditorium. And we can imagine these are in thousands of dollars. So it seems like a realistic amount to pay for an auditorium. So what we're going to show here is that the greedy choice, and we can define a greedy choice a couple of different ways, but the greedy choice won't work here, and that we've got to use dynamic programming. So first of all, we want to look at what is our choice situation. And again, in economics, we say you make choices on the margin. So we're faced with a situation, for instance, let's say it's noon, and we're looking whether to schedule the noon event or not. Well, what are our options here? Given that the events run 3 hours, what we're going to have to look at is we could choose the noon event, but then we have to forego the events that might have started in the 2 hours before the noon event. So the latest previous event we could schedule would be the 9 o'clock event. Or we could take the best scheduling we have up until 11 and forego the noon event. So this is our choice on the margin here. And this exhibits optimal substructure, something characteristic of dynamic programming, because if we assume we're going to take the noon event, then we have to make the optimal choice amongst events starting at 9 or earlier and events starting at 3 p.m. and later. So what we're left with, given we assume this is in our optimal choice set, we're going to have two subproblems that also exhibit optimal structure. So let's devise the recurrence for this. The optimum at n is going to equal the maximum of, we'll call this array P for prices, the maximum of P sub n plus T of n minus 3 and T of n minus 1. So having devised our recurrence, we could now write a very straightforward recursive program to solve this problem. However, since we have overlapping subproblems, solving T of n minus 1 is necessarily going to involve solving T of n minus 3. This is the characteristic of overlapping subproblems, and as we've seen when we studied, for instance, the Fibonacci sequence, when you have overlapping subproblems, a straightforward recursive solution is very inefficient. We tend to get exponential runtime. We can use a recursive solution and memoize it, but we're going to look at how to do a bottom-up dynamic programming solution. What we're going to want to do for our bottom-up solution is move along the array in this order and continually ask what is the maximum revenue we can gain by making the choice at the point we are in the array or foregoing that choice. And we're going to keep this efficient by recording at every hour what the maximum is for that hour. We're also going to use a trick that the authors of our book like very much. We could make a special case for 8 a.m., but we can keep our code cleaner by extending our arrays back 3 hours. And we've got 7, 6, 5, and just put in zeros. And this way we can march forward and not worry about a special case for the first possible event. Because we couldn't look at T of n minus 3 here unless we filled in some zeros. So this is why we can, with this structure, we can now run this code and we come forward and let's make another array and put in our maximum at every point. So we can start our code here. So we can pass in a starting time. And what we're going to do is look at the maximum of this event plus this or here. So clearly, this is what our zeros are for, so we can do the same computation at each step. So clearly the maximum here is 2. Now we're going to, our black color is a little faded here. Let's get a new color. So we're going to do a maximum of 2. We come to the next hour. So now we have a choice. We can do the maximum. We can schedule this event and have the maximum we get 3 hours before. So we can have 4 plus 0, or we can have the maximum of 1 hour before 2. So again, clearly, we're going to take the 4. We proceed on. We now have someone bidding 8,000 at 10 a.m. We can take this and the maximum 3 hours before, or the maximum of 1 hour before. We're going to take this. Whenever we have no bid, we simply have the maximum of the previous time, because obviously there's nothing new to calculate here. Now things actually get interesting, and we have an interesting choice to make. We have a $7,000 bid at noon. And if we need to output what times, we can have an auxiliary data structure that here records that this involves 9, this involves 10, this involves a choice of scheduling at 10. So now we have the choice. We can schedule this and get the maximum of 3 hours before, or we can take the maximum of 1 hour before. In this case, it's better to schedule this and forego this, because we get a total of 11. 7 plus the maximum here of 4. Now we have a choice of scheduling this and getting the maximum here, or taking the maximum here. In this case, we've got a tie. So our code is going to have some way to do a tiebreaker, flip a coin, something like that. But in either case, we're going to get the answer of 11. Okay, we're looking at scheduling at 2 p.m. We can take 3 plus the maximum of 3 before. We get another tie, don't we? Now again, we have an interesting choice. We can schedule a $7,000 event at 3 p.m. or we can take the max and get the maximum up to noon, or we can take the maximum up to here. We're going to go ahead and schedule that event. We get 18. We have one final event, 4 p.m. We can schedule this event and take the maximum of 3 hours before. That's only 16,000. We're better off not scheduling that and having the 3 p.m. event scheduled for a maximum revenue of 18,000. Now it's important to note here that making the greedy choice, and I can think of 2 possible ways we could define the greedy choice here. Both of them fail to achieve the optimum. We might try the same greedy choice that the activity selection problem has. Choose the event that ends first. So we choose this event. Unfortunately, there's an opportunity cost to choosing this event. We've blocked this event. So let's look at what our optimal solution here is. We wind up, our optimal solution is the events at 9, at noon, and at 3 p.m. So that's optimal. If we choose the activity that ends first, we're going to block ourselves from getting this 4,000. We're going to wind up at 16,000 instead of at 18,000. So the greedy choice made as in the activity selection problem will not work. Another possibility, you might say, Professor, it makes more sense here to define the greedy choice as let's grab the highest bidder first, accept the highest bid, and then see what else we can do. Well, the highest bid is our 10 a.m. event for $8,000. And notice that again, this is not part of the optimal solution. In fact, choosing that event will block us from getting this one, and we'll wind up again, as we see, we wind up at $16,000 instead of at 18,000. Because if we choose this, we also can't have this event. So we wind up foregoing this and this event in order to choose this one. And we wind up $2,000 poorer as a result. So this is how we go about devising a solution to a dynamic programming problem, and hopefully this gives you an understanding of when we can't use a greedy algorithm and we have to use a dynamic programming solution instead. It involves the idea of opportunity cost. All right, thank you.